Okay, are you all ready? Okay, from day one, right? I'm seeing all of you in the same place. So for a change seats. Okay, at least move 5 seats away from where you are seated. Okay, do that now. Change seats. At least 5 seats away from where you are seated. Yeah. Okay, so during my lecture this morning, I was referring to a domino video. So this is that video. Maybe you cannot hear the sound because the connection is VGA, right? VGA, yeah. Anyway, you can understand what's happening. Subtitle, no, I'm not playing YouTube. But anyway, you can understand what's happening. So, this is a rough analogy. Whenever we give analogy, we have to say in which way it is correct, which way is not correct, right. So, not everything about this is correct in what we discuss. I mean, if we go by this analogy, right, you may start with a 5 kilowatt anisotropy field material to all the way even up to 1000 kilowatt, but it does not happen like that. We can go somewhere from 5 kilowatt to maybe 15, 20 kilowatt, not too much. Okay. So, that is where the analogy ends. But in this case, there is no limit. You can go even higher. You can scale the domino to even larger sizes. And if you watch the video, I think you will say you can go to the height of some tall towers in New York. Okay, all the way you can make them fall down. So, I will do a recap of where we left this afternoon. So, we started looking at the perpendicular recording technology, and we moved to perpendicular recording technology to overcome the writability issues. So, we learnt about media trilemma. So, for reading, I mean, to get high SNR, we need small grains, but with small grains you have thermal stability problem. So, you can overcome the thermal stability problem if you choose a high anisotropy material, but you will have writability issues. So, we always focus on tackling the writability issues. Once you tackle writability issues, you can move to high density. So, perpendicular recording technology is one way we can tackle the writability issues. So, I told you that by using a combination of a single pole head and a recording media with a soft layer, soft underlayer at the bottom, we can generate larger magnitude of magnetic field to reverse the grains. Okay. So, that is where we started the perpendicular recording topic. Then later part I taught you the different layers involved in perpendicular recording medium. So, we start with the substrate, then we deposit an addition layer which is like a glue for all the other layers on top. Then we start with the soft underlayer. So, I told you we need at least 3 layers to minimize the noise related to soft underlayer. And I also told you that this soft underlayer has a radial anisotropy. That means the magnetization of this soft underlayer is always going to be like this. Okay. So, if you have a disk, if you do not apply any magnetic field, the magnetization of the soft underlayer will be pointing along the radial direction. So, those are the techniques people use to reduce the noise from soft underlayer. Then we talked about the seed layer. Seed layer helps to achieve C axis orientation for ruthenium, and we need 2 ruthenium layers because this gives rise to good C axis texture, and this layer is sputtered at high pressure. It helps to segregate the grains, and the recording layer also is sputtered at high pressure, so that the grains are segregated from each other, and we use many layers to improve the writing performance. So, I told you you used the domino analogy. So, we have many layers, high anisotropy layer is at the bottom, a low anisotropy layer is at the top. So, when we apply magnetic field from the top, the magnetic field will first reverse the low anisotropy layer at the top, and the reversal will cascade all the way to the high anisotropy layer. So, this is what we learnt, and this has been a progress for many years. Still we will end up with some problem. Okay. So, after some time you will again end up with some writing problem. Okay. So, one technique that people proposed to overcome the writability problem further is called shingled magnetic recording. Okay. So, when I started teaching the recording media the recording basics, so I told you that we will have a track 1, then there will be track 2, track 3 and so on. Okay. So, I told you that within this track there will be bits okay. So, each track is written by this head. Okay. So, the track width is determined by the size of this head. Okay. So, if this head is like 50 nanometer, then your track will be 50 nanometer, something like that. So, this has been the technology for many years, but the problem happens when we make this size smaller. Okay. So, long ago when the tracks were 100 nanometer wide, if the tracks were 100 nanometer wide, this was 100 nanometer. Okay. For example, this area will be larger, right. So, for long time the head used to be wider because the tracks were wider, but as you make the tracks narrower and narrower, you make the head smaller and smaller. Okay, so, if you take a big magnet and small magnet, so you know that the big magnet will produce very strong field, the small magnet will produce small field. Right? So, when we go towards a small track, narrow track width, then we end up again with the writing problem. So, less magnetic field. So, again writability becomes a problem, because we want to make many tracks in a given area. So, going from inner diameter to outer diameter, we want to squeeze as many tracks as possible. For that we have to make the head smaller, but when you make the head smaller, you have writability problem, because the field becomes less. Okay. So, to overcome that problem, people came up with this concept called shingled magnetic recording. Okay. So, normal method is like you write one track, then move the head to here, write this track, and after you finish writing information, you move here, write information. So, that is how we write information, leaving some space between two tracks. Okay. This is what we used to do. However, in the case of shingled magnetic recording, we do not do this. Okay. So, we make the head wider. For example, let us say instead of going from 100 to 50, we just keep this 100 nanometer wide head. Okay. So, how can you make a 50 nanometer track with a 100 nanometer wide head? How can you make? Can you make, first of all? You have a 100 nanometer head, but with that you are making only 50 nanometer tracks. Can you? Okay, you can make Let us say I write one track, the bits are like this. Okay, then I move 15 nanometer and write a new track. Okay. So, whatever is here will get overwritten, then I write some new track. Where the bits may be like this. Okay. So, you keep moving 15 nanometer and start writing track. So, when you do this, this will remain intact. So, this will be intact, but whatever is on this side will get erased. So, it is like doing this, then like this way. Okay. So, you write just by shifting certain distance. So, that technique is called shingled magnetic recording. So, you have a wide head, you write bits, but move only a little bit. Okay, so, now the head size is bigger. So, since the head is wide, you can have large field. So, no writing problem, but there is another problem, right. What problem do you see here? Hmm? So, after lunch I asked you to move around, so that you are alert. I mean, okay, ignore what is this corner, just it's a perspective issue. So, it's like we write one track, another track and so on. So, if you look from the top, it will look something like this. So, you have one track where you have some bit. So, the next track you start from here, maybe this becomes white, this becomes dark, something like that. Okay. Do you find any problem with this? Okay, so let me explain first. So, in this method we are using a bigger head and write information by overwriting. So, if you just do not do anything, your tracks will be wide, but you are shifting by a short distance and you are starting the next track and so on. So, this way you see with a wider head you can make smaller tracks. So, here the field will be larger because the head is wider, but the main problem is in the case of the conventional technology, right. Let us say you want to write some new data in this track, you can write in this track without affecting any other track. Okay. But here, for example, let us say you want to write some data here. Okay. When you write data here, you will erase the data here. Okay. So, that is the problem. So, people store information in a group of tracks called bands. Okay. So, we will have certain band that goes from this radius to this radius. So, within this you have like many tracks, then you will have some gap between the two bands, then here you will have another band where there are many tracks. So, if you want to erase or write any information in this track, right. So, you have to write this whole band. So, that is the only problem, because when you write information in this track, you are erasing the information in the other track. So, you have to read and write the same back the same data. That was the only problem, but otherwise this technology is now being used. Okay. So, if you own some hard disk drives, maybe this technique is already there. Any questions? Is it clear? I mean, looking your silence, I am worried whether you understood or not. Should I ask you to go back to your seat? Okay. Now, let us move on to another technique. So, with all the developments that we discussed, all these layers, and with the single magnetic recording, we have gone all the way to like 1.5 to 2 terabit per square inch. So, if we want to go further, we need some other technologies. Okay. So, what if we go further? Let us say your HK is like 1.5 Tesla and so on we have been using, but there are materials like iron platinum, L10 iron platinum with HK of 7 Tesla. Okay, there are many materials like iron platinum, cobalt platinum with a very large anisotropy field. Okay. So, these materials have a very large Ku. That means, you can make the grains even smaller and we can achieve much higher densities than what we can achieve. Okay. So, let us say that the coercivity of the iron platinum is 7 Tesla or 70 kiloohrsted, but we have a right field of only 15 kiloohrsted. So, how do we write information on this? Okay. So, for this question, one answer is the heat assisted magnetic recording. So, you all know that when we have a ferromagnetic material, if you measure the magnetization as a function of temperature, the magnetization will drop, and at Curie temperature the magnetization will be lost, right. So, in a similar fashion, anisotropy also gets reduced. As you increase the temperature, the anisotropy will also get reduced. Coercivity also will be lower if you raise the temperature of the sample. So, heat assisted magnetic recording tries to use heat. I mean, you heat the sample and do the recording, then remove the heat, then you store the information. Okay. So, that is the concept of heat assisted magnetic recording, but we want to have smaller sizes, right. We are storing information at high density. So, you cannot put your disk in the oven. Okay. So, you do not want to put your sample in the furnace, you want to heat locally. So, we use lasers focus to small spots, heat them, then write information, then when the disk moves away from the laser, it will cool down. Okay. So, that is the concept of heat assisted magnetic recording. So, let me show you the video. So, you have a disk and you have a head. So, if you just try to write normally, you may not be able to reverse the magnetization. On the other hand, if you focus with a laser, you are then goes down and the writing field is enough to switch the magnetization. So, this is the concept of heat assisted magnetic recording. So, people are using material with a very large anisotropy like iron platinum to achieve the heat assisted magnetic recording. Okay, so, the head will be very similar to perpendicular recording, except that there is an additional laser. Okay, there is a laser beam. So, the laser beam will shine on the recording media, heat a small region. So, that small region will go to a high temperature. So, coercivity will be reduced. So, even though your head is, your head has only 1.5 Tesla field, the coercivity will be reduced to much smaller values, okay, because of the temperature. Okay, so you can write information. So this concept was proposed like many years ago, like 26, 27 years ago, people started working on this, and there were many challenges. For example, I told you that recording media, on top of the recording media, there is a polymer, right? A polymer serves as the lubricant, but when you heat with a laser, this heating is around 600 degrees Celsius, 500 to 600 degrees Celsius or Kelvin, I do not remember. So, it is a very high temperature, not like 100 degree or 200 degree, around 400 degrees Celsius. Okay, let us say 400 degrees Celsius, the lubricant cannot withstand. So, you know that if you have polymer, you heat at 400 degree, it will not be stable. Okay, so the lubricant will be gone, and when you heat the carbon overcoat at this temperature, carbon overcoat will be spoiled, and so on. So there are many such problems. So recording media design also is a challenge. You need to make the sample at high temperature. Again, you have to. So far, we have very well established how to grow perpendicular media with isolated grains. So all those things we need to do all over again. So how to make the iron platinum grains to be separated from each other. So all those recording media principles have to be redone all over, start from scratch, do many things. Then the main problem is the laser beam. Okay. Suppose you have a laser beam with a 400 nanometer wavelength. So which laser has this wavelength? Which color laser has this wavelength? Blue. Okay. Let us say blue laser has this wavelength. What will be the smallest dot you can achieve with this? Smallest dot, yes. So if your laser has a wavelength of 400 nanometer, what is the smallest dot you can achieve? You have studied optics, right? So in the far field optics, if lambda is 400, what will be the smallest spot size? So it's typically lambda by 2. Okay. So the smallest spot you can achieve is 200 nanometer. Okay. So now we are talking about 50 nanometer track width, but if your laser can only provide 200 nanometer wavelength spot size, then there is no use, right? Then it will be like 2D material, promising but no use. Then what can you do? Okay, so I mean, when people propose this kind of technology, there will always be some questions. How are you going to make the lubricant? Lubricant will evaporate. How are you going to solve that problem? Laser beam will have only 200 nanometer spot size. How can you make the tracks narrow? So all these questions will be asked, but you have to think whether all those can be solved. Okay, so people developed lubricants that can withstand 400 degrees Celsius. So there was progress here. Then people made recording media better, and for this problem, people worked on some near field transducers that can help to achieve the laser spots even below 200 nanometer. Okay. I do not know how many of you heard the word plasmonics. Huh? Okay, so when you have let me see whether I can switch to another presentation. Okay, so let it download. In the meantime, so I will come to the plasmonic aspect after the file gets downloaded. The internet is anyway, I will discuss that once the file gets downloaded. So, they used some concept called plasmonics to solve the problem. So, with that plasmonic technology, they can make the spot size even smaller than 200 nanometer. So, because of that now they can make a product using heat assisted magnetic recording. So, as early as 2018, Seagate has announced 16 terabyte hard disk drive. Okay. Now, there are Hammer heat assisted magnetic recording hard disk drives with a higher capacity. Okay. So, this is a video of how it works. So, you have a head and you also have a laser beam. The laser beam hits the sample, and when the sample gets heated, you write using the head. So, this is the head that writes the information. Okay. So, we generate magnetic field somewhere here, write information, and as the disk passes away from the laser, it will get cooled. So, you heat, write information, and when the disk goes away from the laser beam, it will get cooled and the information will be stored. So, this is called heat assisted magnetic recording. So, while we wait for this to get downloaded, any questions? Now, we have almost covered everything. So, you can ask any question related to anything. So, have you got all the information you wanted? You wanted to know the materials? Okay. Okay. We don't, first of all, there is no domain, right? So, number of grains or grain. Okay, so firstly, we do the, in perpendicular recording technology, we do the high pressure deposition. Okay, high pressure deposition makes the material, the grains to separate from each other. Then we choose proper segregant. So, I told you that we have some oxides, silicon oxide, tantalum oxide, and so on. So, your target will be something like this. So, cobalt, chromium, platinum, then some oxides. Okay. So, when you deposit this material at room temperature in the present, I mean with some oxides like this, the grain is magnetic and the grain boundary will be non-magnetic. So, it is by these two combinations. Yes. So, this is how we make the grains smaller. So, when this, I mean these grains are like 8 nanometer kind of diameter. So, when a cobalt grain is 8 nanometer in diameter, there is, it is not multi-domain, it is a single domain particle. FPT is almost ready. I mean, the companies can sell a few thousand of hammer drives. Okay, now the file is ready, but before that, any question? I will come to your question later. Any other questions? Okay, if not, let's move on to this. So, we all learned this already. So, we do scaling to go towards high density, thermal stability we learned. Okay, so, when it comes to heat assisted magnetic recording, we follow this property. So, if you plot the coercivity as a function of temperature, it will reduce at certain elevated temperature. Let us say your head can produce a magnetic field as high as this one. Then if you operate in this range, the available field is more than the coercivity of the material. So, you can write information. Okay. So, that is the concept behind heat assisted magnetic recording. So, when we want to write information, we go to high temperature and write the information, and when we want to read the information, we just cool. I mean, we do not need to cool or heat, the disk is always rotating. Only when the laser is on, it will get heated. Once the disk moves away from the laser, it will cool by itself. So, we do not need to make special efforts to cool. There are some designs in the recording media itself. So, we have a heat sink layer in the recording media that will cool the disk. Okay. So, this is how we write information. So, this is one of the very early demonstration of heat assisted magnetic recording. So, in this experiment, what is happening is that the writer is always on. So, the writing head is powered on. So, sorry, I mean this part nothing, this period from here to here, the head field is on. Okay, nothing happened. Okay, no information is written, but during this window the laser is on, then you see some information is written. It looks like noisy for you because this is high density information. So, if you look at the oscilloscope, you will see that it is like noisy, but this is all data written. Okay. So, when the laser is on, we can write information. Only when the head is on, we cannot write information. So, this is a demonstration of heat assisted magnetic recording. So, this slide we have already seen. So, the question is how narrow spot we can achieve. Okay. So, I told you the current technology is somewhere here 12 nanometer, 14 nanometer. So, if we have to make hammer better than the current technology, we have to make the spot size smaller than 50 nanometer. Okay. So, this is the challenge, and this comes from the diffraction limit. Okay, so, people try to do something called near field transducer first. For example, if you make a very small hole inside some metal screen, even if your focused spot is 200 nanometer. So, let us say you produce 200 nanometer spot, but this hole is smaller than 200 nanometer. So, in this case the light will produce much smaller spot, but the problem is the temperature that you can achieve will be very small, because the transmission radiation scales with R over R power 4. Okay. So, if R is the whole size, then the radiation will be smaller in size, I mean much smaller radiation. You block most of the light, you do not have much light to heat the material. So, this is not very useful approach. Okay. So, then somewhere in the 1990s people came up with some progress in optics called the surface plasmons. Okay. So, I do not exactly understand how it works. So, what happens is that let us say you make a lollipop type of material like this, you shine this material with light, then these surface plasmons are created. Okay. So, I will ask you to read, because I do not know much about this field. So, because of this surface plasmon, at the end of this lollipop shape, you can produce narrow light with high intensity. Okay. So, even if this spot is only 50 nanometer, because of this material, you can get very high intensity small spot. Okay. So, people have researched a lot of near field this kind of transducers. One is a lollipop shape, then bow tie shape, C aperture, and so on. So, people have looked at various such transducer. So, because this surface plasmon thing, they can achieve high density light beam with smaller spot size, smaller than what you can achieve in the far field optics. Okay. So, because of that now people can demonstrate hammer, and one problem for very long time has been the life of the transducer. Okay. So, you keep heating this surface plasmon. Let us say initially it is let us say this made of gold. Okay. This lollipop was initially made using gold, and let us say initially your grains in the gold were 20 nanometer in diameter. Okay, then you get some property. Okay. So, initially the let us say the properties are good, but what you are doing, you are shining laser, laser will heat this lollipop. So, as you keep annealing a material, what will happen? So, when you anneal a material, basically the grain size will be changed. Okay. Maybe the grains would have grown to say 200 nanometer, then the property becomes different. Okay. So, as you keep heating this material, its property changes after some time, then it does not generate the surface plasmon anymore. Okay. So, we can't write information. So initially this transducer life was like a microsecond, then people slowly improved to milliseconds, seconds. I think now the target they have for this is more than 1000 hours, something like that. Okay, so there is a lot of work going on to improve the life of the transducer. Okay, that's all for hammer. Now we are somewhere in 2 terabit per square inch, somewhere here in this range. Less than? Second last slide. This was I mean I made this slide in 2015. Very old. 10 years ago I made this slide. You see the style is different, right? This is why my current slides are like this. Yeah, that is very old slide. At that time, yes, maybe like this. Yeah, we have already exceeded all those. Yes. Okay, any questions? Theoretical. Okay. Mm. Mm. Okay, let me. Okay, I may not have slides, so I'll just use the board. Anyway, finally, what will determine the ultimate limit is the thermal stability, right? Okay, so the best known material is iron platinum. So for future recording, there is only one material available for magnetic recording. So if anyone says that I have worked on nickel something and I have a material for recording media, that is just BS. Okay, that's not correct. The only material that is usable for future recording is iron platinum, because we need high anisotropy to make the bits smaller, and we need a high ms so that your HK is not too large. Okay, HK is 2 Ku over ms, right? So if ms is small, then your HK is going to be large. So again, useless. Okay, the only material that can meet future requirement is iron platinum with this high anisotropy and high saturation mineralization. So with iron platinum, you can make even 4 nanometer grains or 4 nanometer dots. Okay, so there is some technique called heated dot magnetic recording. Okay, so you already know what is heat assisted magnetic recording. So we use heat to write information on materials like iron platinum with a high anisotropy constant. Okay, so when we come to heated dot magnetic recording, what we do is like instead of a disc where you have iron platinum film, you will have a disc with islands of magnetic materials. So you will have small dots. Okay, so each dot will be 4 nanometer in diameter. So you will have many such dots, and if you do this, then the areal density will be roughly 10 terabit per square inch. Okay. I mean, this is the most practical possibility, but even this is like very difficult. Okay. So, can you make 4 nanometer dots over a disk uniformly, and these dots have to be perfectly arranged. Okay. So, they have to follow certain sequence. You cannot have like one dot here, another dot here, then another dot here, like that. They have to be like very uniformly arranged. So, patterning them is difficult, very expensive. So, even this is like almost impossible. Yeah, I think that's all. Yeah. 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 I mean, theoretically, you can say so many things. Even this is like very difficult. Good morning. Okay. Anything else? Any questions? Let me see whether we have covered most of them. Okay, this is supposed to be ABC of magnetic recording. When we wrote this proposal, right, there was one faculty here, Surbi Gupta. She was my postdoc, and we wrote this proposal at first. So the idea was I teach on magnetic recording and she teaches on spintronics. But since she has left, and I covered, I mean, I spent most of the time on magnetic recording. And if you want to learn the spintronic aspect, so I have given another Gyan course in IIT Guwahati, where I spent 10 days teaching spintronics. Okay. So, those spintronics lessons are more detailed. Okay. So, one attendee is here. So, he attended the 10-day Gyan workshop. Yeah, it will be like this. The connection is very Airtel. Okay, then you need please type the password. Okay, connected, now connected. Okay, so it was a 10-day workshop. So I taught like 10 continuous day, no break, every day 3.5 hours. Okay, so you can watch this set of videos. And this Gyan also is already available, right? Yeah, so day 1, day 2, day 3 are already available. So please watch before tomorrow's test. Okay. So most of the questions will be based on the book lab. Okay. Okay. Any more questions? Okay, if not, we'll end here. Tomorrow I'll touch upon the carbon overcoat, lubricants, and some other topics. If you have any questions, please come prepared and ask me. I'll be here for maybe 1.5 hours, then leave. Okay. Okay, see you tomorrow. Thank you.